All right, so yesterday we finished up talking about Gilbert Lewis and how he didn't win a Nobel Prize, despite contributing a lot to organic chemistry. And we started talking about Lewis dot structures. Most of you have seen this in Gen Chem, I would imagine, and spent some time on it. But we're going to do a little bit more practice. Like I said, the key rules with Lewis dot structures is ideally you want to pair electrons, unless we're talking about radical chemistry, which we'll cover second term. Ideally, you want your atoms to have 8 electrons around them. However, like I said, that's more a general guideline, not a firm rule. And you want to include formal charges on specific atoms. So what we're going to do is we're going to do some easier practice ones, and then we'll build up to harder ones, and then I'll let you work on the pod a little bit. So let's do a first practice problem. The first one I want us to do is HO minus. It's a hydroxide anion, your favorite one that you titrated with all last year or in previous years. If we try to do Lewis dot structures, the easiest way, the most elementary way to do it is to draw your individual atoms first. So down here I'll draw a hydrogen. And hydrogen has how many valence electrons? 1. Okay. And then over here I'll do oxygen in red. How many valence electrons for oxygen? 6. So I'll go 1, 2, 3, 4, and then pair 5, 6. Okay. Now what we want to do is we want to try to pair up electrons so that the atoms are happy, right? So what I can do is I can say, all right, we can pair those 2 electrons and form a bond. That's going to be a covalent bond because we're sharing them. All right, so if we go ahead and we do that, now we can go ahead and we can say, all right, we're going to form a covalent bond to that oxygen. Let me actually keep it color-coded. However, if we look at this oxygen, it doesn't look super duper happy, right? What's the problem? It's missing an electron. So one problem is this electron right here doesn't have a buddy next to it. It's missing a partner. So that's one problem. The other problem was we didn't have a total of 8 electrons around it. It really wants 8 electrons. So what we're going to do to solve that is we're going to take an electron from some sort of external source, at least that's what I'm calling it. We're going to shove it in to that spot so that that oxygen's happy. Okay, so when we go ahead and we add that electron, that oxygen now has an extra electron that it formerly didn't have. So therefore, we want to indicate that it has a charge. Specifically, this oxygen is going to have a negative charge. So if we go ahead and we draw the Lewis dot structure for the hydroxide anion, it's going to look like that. Makes it really easy to predict formal charges when you structure it this way. Let's try another one. We'll do another ion. So we'll do the NH4 plus cation. What's this one called? Anybody remember? The ammonium cation. Okay, central atom's going to be nitrogen. So I'll just put nitrogen right here. Actually, let me move it over some more. How many valence electrons? 5. So go 1, 2, 3, 4, 5. We've got 4 hydrogens, so I'm going to try to stagger those hydrogens evenly around the nitrogen. So I'll go 1, 2, 3, 4. Each of these hydrogens, like we saw before, has 1 valence electron. I'm going to actually space these pairs out a bit more. Okay, so we're set to go, and we're going to pause for a few seconds before we continue on.
Pause for the fun stuff, right?
Yeah. All right, so going back to the ammonium ion, we've got 4 hydrogens, each with 1 valence electron, and we've staggered those evenly around our central nitrogen atom. Now what we want to do is we want to pair them up to form bonds. So I'll go ahead and form a pair there. I'll form a pair there. Form another pair there. And here's the tricky part. We've got this hydrogen up here, but this nitrogen has a lone pair. Doesn't matter. That hydrogen wants to form a pair. So then what we've got to do is figure out the problem. Problem is that central nitrogen, how many electrons does it have around it? 9, and one of them's unpaired. That's okay, because what we'll do with the magic of chemistry is pull this electron away from that nitrogen. And when we do this, now we have nitrogen with 4 bonds to hydrogen. And because we pulled that electron off of nitrogen, that nitrogen by itself has a positive charge. So we like to show the charge being off of the nitrogen. One thing I've noticed, depending on where you took general chemistry, is some students have seen the ion written this way. So let me redraw it slightly differently. Or maybe it's in brackets, or you see a little upper bracket like that with the plus sign out there. The reason I don't really like this method is it doesn't indicate where the charge is, right? It just says this has a charge somewhere. It doesn't tell you very much. So organic chemists really like to show the location of a charge on a specific atom. So that one's really not preferred. I'll just go ahead and erase it. All right, let's try a harder one. This time we're going to deal with bonds that are a bit more complicated than single bonds. So this one's Cl2. This is phosgene. Do we have any history buffs in here? Yeah, it was used in, it's not the same as chlorine gas that was used in World War I. This was another World War I gas. Pretty nasty stuff. It's different than mustard gas too, but it's pretty nasty. When you breathe it in, it will react with the lining of your lungs and basically blister you from the inside out. Pretty horrific war gas. It's still used on massive industrial scales for plastic productions, though. They just have to be very careful when they work with it. So I'll give you a hint with this one. So when we do this, carbon, like I said, is the backbone. We like to put carbon in the middle of things. All right? That means the leftover atoms are 1 oxygen and 2 chlorine. So I'll go ahead and stagger an oxygen here and 2 chlorines over here and here. Doesn't really matter how you orient them. I like to stagger them so that they're all not lumped into one corner. It's just easier. Okay, oxygen should have 6 valence electrons. So I'll go 1, 2, 3, 4, 5, 6, like that. Chlorine should have 7. So I'll fill in both of these chlorine atoms, and there we go. So we can go ahead and work on the chlorines first. We want 8 electrons around each. Pretty easy. All we need to do is form a bond to that carbon. Same thing with this chlorine. And then we need to link up the oxygen with the carbon next. So we can go ahead, form a bond right there. But if you look at the oxygen, it has an unpaired electron. Also doesn't have 8 electrons. Same with the carbon. It only has 7 electrons, one of which is unpaired. So we can go ahead and link both of these together. If you notice up here, there is no indicated charge, so we're not going to be adding atoms or adding electrons or removing electrons from this. So we can go ahead and make this a little nicer looking. We can have a carbon there, double bond to oxygen, 2 chlorines here and here. And there we go. This is the structure of phosgene gas, the chemical weapon used in World War I. Does that make sense? All right, let's try a little bit harder one. This time, we have to determine the charge on specific atoms. And I want you to also work on the Lewis dot structures. So the first one is AlH4, and we don't know what the charge is, but hopefully you can figure that out. So I'll just put a question mark up there. That'll be the first one. Next one will be Cn. I'll do a question mark here. And then the last one is going to be BnH6. And we don't know what the charge is on that one either. So what I want you to do is try to draw the Lewis dot structure and anticipate whether or not you're going to need to add or remove electrons from specific atoms in order to make things work. So I'll give you a minute to work on this. See a show of thumbs. How many of you feel confident that you got one of them? That's some hands, but that's okay. How about 2 of them? Keep your thumbs up. How many think they got all 3? All right, let's try this really quick, and we'll walk slowly through this, so don't panic if it doesn't make intuitive sense at first. So we'll start with AlH4 first. We've already seen hydrogen has one valence, so I'll go around and give each of these hydrogens one valence electron. How many for aluminum? 3. So I'll go ahead, go 1, 2, 3. And then what we want to do after we've added in all those electrons is try to pair them, right? So I'll go ahead and I'll say, we compare these two, form a bond. We compare these two, form a bond. We compare these two, form a bond, but uh-oh, we've got a problem. What can we do to fix that? Add another electron. So I'm going to toss in one extra electron to that aluminum. That way it has enough electrons so that it can not only have an octet, but form a bond with that fourth hydrogen, right? So if we think about this, if we go ahead and we draw this, we'd say Al is bonded to 4 hydrogens, like that. And the formal charge, what would that be? -1 on the aluminum, right? So you can write -1. Usually if it's -1 or +1, you don't include the number because it's just implied. So I'll just write Al negative like that. So there we go. We've drawn the Lewis dot structure of aluminum hydride. That's the name of that anion. All right, so let's do the next one, Cn. Carbon we know has 4 electrons for its valence, and nitrogen has 5. So let's go ahead and try to pair all of these up. So just like before, we can say, all right, pair that up. We've got a bond. We can make more than one bond, so let's do a double bond right there. Again, we can try to pair these up. All right, we're close. The nitrogen now has all its electrons paired. The nitrogen also has an octet of electrons around it, but the carbon doesn't. So what can we do? Add an electron. So what I'm going to do is toss one electron into that carbon. So now when we go ahead and we redraw this, we've got a carbon-nitrogen triple bond. The nitrogen has a lone pair, so we want to show that. And then the carbon also has a lone pair, and we want to show that. The negative charge is located on what atom? Carbon, exactly. That's why I really like showing where the charge is. That way you don't inadvertently think that the nitrogen's carrying the negative charge. It's more on the carbon here. Make sense? All right, so now the hard one. BNH6. Each hydrogen has one valence. So I'll go ahead and do the easy ones first. Boron, how many does it have? 3. So I'll go ahead, 1, 2, 3. Nitrogen has 5. So I'll go 1, 2, 3, 4, 5. This one's got a lot more going on, but let's do the easy stuff first and then fix our problems later. So we'll start pairing up electrons. Hydrogen's easy to pair, so let's go ahead and pair those 3. However, the boron can't bond to the nitrogen, so we're going to have to add an electron, right? Not only so that that boron has an octet, but so that it can actually form a bond that's needed. So I'll go ahead and toss this in and say, all right, that boron's going to be given 1 extra electron. Now we're in good shape to pair up the boron and nitrogen. Okay, now we'll do the nitrogen. It can bond to this hydrogen through a pair. It can bond to this hydrogen with a pair. And then over here, what we're going to do is pair up this hydrogen. We know we have to make a bond, so we've got to do that. However, this electron right here is over the octet rule, so we're just going to pluck this out and remove it. So let's go ahead and draw the Lewis dot structure. This is where it gets tricky. The charge on the boron is going to be what? Negative. We added an electron to it, right? To form that bond. So I would say negative. Put that right there. What about the nitrogen? Positive. What's the net charge of this overall compound? 0, right? This is weird. This is called a Zwitter ion. A Zwitter ion is a molecule that has a positive and a negative charge, but a net charge of 0. So it has ionic behavior, but isn't a true ion, right? It's a little bit odd that way. Cyanide is an anion, and then aluminum hydride is also an anion, and like we saw before, you can have cations. Zwitter ions are kind of the oddballs of the group. Does that make sense? Okay, so for the next challenge, what I want you to do, before that, yeah.
So nitrogen is more electronegative than boron, so why would nitrogen give its electron per boron and have one?
That's a good point. So the question was, isn't nitrogen electronegative? Why would it ever want a positive charge? In general, atoms prefer to have an octet more than they prefer to follow electronegativity trends. It's kind of odd that way. Yep.
And is it also reasonable to structure it with pair 4 of the hydrogens with the nitrogen instead of only 3 and 2 with the boron?
So you were asking, what if you have 4 hydrogens bonded to nitrogen? If you were to do that, nitrogen would have an octet and couldn't bond to the boron. So it wouldn't be one molecule, it would actually be 2 different molecules.
But it means 5 bonds, right?
So nitrogen would only have 4 because each bond has 2 electrons, so 2 times 4 would be 8. If you have more, then you'd be over an octet. Yeah.
When you're starting just with your valence electrons, can you get to the same conclusion by like bonding the nitrogen and the boron first and then doing the hydrogen?
Yeah, definitely. You can do this a lot of different ways. I like doing it really elementary because it's easy to see, hey, I need to add an electron here, therefore it has a negative charge. I know some of you learned different methods in Gen Chem. If you have another method that works for you, go with that method. This is the way I like doing it. Yeah. Okay, so, yep. So that's a good question. Can you have a quadruple bond? In general, no. In organic chemistry, we deal with single, double, and triple bonds. You won't see quadruple bonds until you get into inorganic chemistry. Good question, though. It is possible. There's a lot of goofy bonds when you get into d orbitals. We're not dealing with d orbitals right now. Yeah. All right, so let's pull up the problem of the day, and I want you to work on the Lewis dot structure portion, and then check with your neighbor and see if you're getting the right answer. This one's a little tricky, and I will give you a hint that there's a nitrogen-nitrogen bond in that structure. Do you guys want to hand it in for points? Or would you rather just not be worth anything? All right, you can hand it in for points. Hopefully everybody gets 100%. It could just be participation. If you think you got it too, I'll throw you an additional challenge. There's actually 2 different ways to draw this molecule. Both structures still have a nitrogen-nitrogen bond involved, though.
There is one.
Yeah. So I'll give you a hint by structurally laying it out, right? Both of them will have some sort of arrangement like this, with a hydrogen coming off the carbons is the easiest way to go about doing this, but sometimes it's a process of elimination system that you have to go through. All right, for the sake of time, I'm going to start drawing in valence electrons on these. We'll do the easy hydrogens first. So 1 valence for each hydrogen. Nice and easy. Carbon. How many should it have? 4. That's nice and easy. So 1, 2, 3, 4. 1, 2, 3, 4. Nitrogen? 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And I'll fill in the rest here. All right, so now we've got a few decisions we got to make. So let's work on the one on the left. For example, I could say, all right, I'm going to pair these up. We know that's got to happen regardless of anything else. Same thing over here. We're going to pair these up regardless of anything else. Doesn't really matter which electrons you're pairing up. I'm just doing this quick and dirty, right? All right, next thing, we'll focus exclusively on this compound over here on the left. So I'll go ahead and pair this one up. Make sense? Okay. So the carbon looks close, but what's wrong with it right now? It's missing an electron, right? It doesn't have a full octet. So over here, I'm going to toss in an electron. So that carbon will have what formal charge? -1, exactly. So we're getting there. Next thing we'll do is say, okay, this nitrogen can bond here. Okay, it still has an unpaired electron, so we'll bond one more. So we'll do that. Okay, now let's focus on the central nitrogen, this one right here. What's the problem? I don't see a problem right now, so let's go over to the other nitrogen. All right, other one. We've got an unpaired electron. In fact, I'm going to move this lone pair over to the far side. Does that make sense? That way it's easier to pair this up. And now you'll see the problem with the central nitrogen. So now we've paired that nitrogen's lone pair on the far side. Now what's the problem with that central nitrogen? It's got too many electrons. It's got 9. So just like we saw before, we're going to take this electron, we're going to pull it out, and what's the formal charge on that central nitrogen going to be? +1. What about the nitrogen on the far right-hand side? So this nitrogen, it's going to be neutral. Okay, so let's clean this up and draw it in a nicer method. So we saw we had a carbon-nitrogen triple bond. Or sorry, a nitrogen-nitrogen triple bond. We had a lone pair on this carbon and a positive charge on the nitrogen. What do we call these when they have both positive and negative? Zwitter ion, right? So this is actually a molecule called diazomethane. It's used in organic synthesis quite a bit. Okay, we did some on the molecule on the right, but now let's finish that up. Okay, so another way you could go about doing this, so you could say, well, let's pair these up and let's pair those up, right? That carbon has an octet in either method. Okay, so the carbon is fine. Now let's do the nitrogen. We could say, okay, let's pair these up and let's pair these up. In fact, I'm going to move the lone pair over here just like we did before, just to make it easier on the eyes. I apologize for changing this. But there we go. All right. Now we've got some problems though, right? What's wrong with that central nitrogen? One too many electrons. So I'll take this electron, pull it away. Now that central nitrogen has an octet, right? Has a formal positive charge because we removed an electron. What about the nitrogen on the right? It's missing one. So there we go. We can toss in an electron right there. So now it has a full octet and it's got all paired electrons. So we can draw it this way. Yep.
When you made the second bond between the two nitrogens, why were you bonding one that was already in a lone pair instead of it?
You have the ability to pick any electrons to pair. So you can do it however you want. Yeah, if that makes sense. So sometimes what you might want to do is move your lone pairs so that they're facing different sides of the molecule. Just make sure you have the correct valence number around the atom you're looking at originally.
I guess I'm confused because before you added the second bond, the middle nitrogen was in octet.
Oh, that's a good point. But if we look at the nitrogen on the right, it was really far away from an octet.
Okay.
So we had to do that eventually, if that makes sense. Okay, so now we've got this. Let's clean this up and make it look nicer. So now we've got two structures. This one that we just made has 2 double bonds in it rather than a triple bond. We said we removed a nitrogen electron from that central nitrogen. So this one would be positive. The one on the right, we actually had to add an electron to. So this would be negative. These are actually both representations of the exact same compound. What these are referred to as is resonance structures, which we're going to be talking about a lot more later. Basically, it just means you have the same molecule, but you're choosing to show electrons in different spots. It's kind of weird that way. So we'll spend a lot of time talking about resonance. All right, so let's, yep.
So the way I had originally did it was I had a hydrogen to a nitrogen, double bond to a carbon, double bond to a nitrogen, bond to oxygen.
Okay, let me see if I'm getting this right. So you had something like this. This would also be acceptable. Without me giving you more information, I would give you 100% credit on this as well. Yeah, good point. So all 3 of these would be acceptable drawings for this. I would give you full credit for any of these. My main concern, especially in first term, is that you are satisfying the octet rules and drawing a reasonable structure, right? So that's all I really care about. Yep.
So then, why are the 2 on the left more acceptable than the one on the right? Or any other drawing?
That's a good point. So you might be wondering, well, why are you preferring the ones on the left? It's because I've done a lot of chemistry, and I know that that's a common reagent. Yeah, that's really it. You should all know that now. Okay, going backwards. We've got to switch gears a little bit and talk about something called isomers. Does anybody remember talking about isomers in their other chemistry class? Anybody remember what they are? Okay, so I heard same molecular formula. That's the key point. So they are compounds. I'm going to abbreviate compounds with the same molecular formula. But they have a different connectivity. Or spatial layout. We'll go over all the different classes of isomers later, but I wanted to introduce you to the most common one that you'll run into, and that's called constitutional isomerism. And they are structurally different. Meaning they have a different connectivity. So the easiest way to remember constitutional isomers is they're just attached differently. So like we saw in that problem of the day, that compound I drew on the far right had a completely different connectivity. It had the carbon in the center. That means it would be a constitutional isomer, although it had the same molecular formula. Okay? So this is one of the main classes of isomers. So let's do an example here. And we'll do the example from the problem of the day. What was that molecular formula? It was C2H6O. So we'll do this one first. I want you to determine 2 different ways of connecting this and see if you can do it in a couple minutes. This one's a lot easier than the last structure we did. All right, for the sake of time, let's go through this really quick. The first one could be presented where you have a carbon-carbon oxygen connectivity like that, and then you space out your hydrogens around it. The other one could be a carbon-oxygen-carbon connectivity. So we're connecting them in a completely different order. The first one, we could say, all right, maybe we're going to have 3 hydrogens there, 2 hydrogens there, and then our remaining hydrogen over here. This is ethanol. everybody's favorite alcohol. It's the drinking alcohol, not methanol, the type that will make you go blind. All right, the one on the right, we're missing 6 hydrogens. In this case, we can have 6 hydrogens where each of them are coming off the carbons. Whoops. And this is dimethyl ether. Not only are they named differently, they have radically different properties. Why do you think that is? Yeah, they can interact with different things, right? I'll give you a hint. What's special about the thing I circled over? Whoa. What can that do where the other one can't? It can hydrogen bond. So some of you might remember that from general chemistry. Don't worry, we'll go back and review all of the intermolecular forces though. So this can form hydrogen bond. The one on the right can't, right? It doesn't have a hydrogen coming off of the oxygen directly. Therefore, it cannot hydrogen bond. Which one do you think will have a higher boiling point? Ethanol. Things that hydrogen bond tend to have much higher boiling points because they're sticky. They stick to each other really tightly. So they have very different properties. So let's make a note of that. Okay. Yeah.
Will they always have very different properties, or is there like an outlier?
They will. Sometimes the differences are extreme. Other times they're subtle. It depends. We'll talk about that in more detail, but they have different melting points, boiling points, freezing points, things like that. So in this case, dimethyl ether is actually a gas where ethanol is a liquid. All right. So we'll spend a lot of time going over isomerism, but this is the type of isomerism you'll see the most when you're just practicing Lewis structures. It doesn't mean you're wrong. Both of these are correct Lewis structures. It just means you attach them differently. You followed the rules that I told you about, though. All right, moving on. We got to review VSEPR theory, or VSEPR theory. Most of you covered this in Gen Chem, if not multiple times before, so we'll go through this pretty quick. But raise your hand if I'm going too fast. Essentially, this arose because there is a problem with Lewis structures. And I'll show you that problem using methane. So methane is CH4. It's the stuff found in natural gas. If I were to look at this molecule, I would say this bond angle looks to me to be about 90 degrees. However, we know experimentally that is not correct. Does anybody know what the correct angle is? Yeah, 109.5, give or take. And a better way of drawing it is more like this, where you draw one of the legs as a wedge and the other one as a dash. The wedge means that it's coming out towards you. The dash means it's going into the page. Does that make sense? So it's almost like a little stool with 3 legs going down and then a hydrogen sticking straight up. And we know this is the case because this allows the hydrogens to be further apart from one another than 90 degrees. In this case, it's 109.5. And the reason atoms like being far apart is electrons have negative charges. They don't want to be close to one another. So this is the correct angle representation for drawing methane. So if you remember, VSEPR theory stands for valence shell electron pair repulsion. Okay, and essentially this helps describe those angles that you're seeing. It basically just says electrons want to be as far apart from each other as possible. And it looks like, again, I was over ambitious with my time. So we're going to have to stop here today. What we'll do tomorrow is, just like today, the pod will be an in-class activity, but tomorrow it will be worth points, so you can hand it in at the end of class and get points from it. Today's pod, since I went through the answers anyway, I just will leave it ungraded in Canvas, if that makes sense. All right, I'll see Tuesday lab upstairs in a few minutes.